Anyway, so let's work with a spherical joint or spherical wrist. So a spherical wrist is basically, the word says it's spherical. Remember, if you have any robot, no matter how complex the joint is, it can always be decomposed as combination of prismatic and revolute joints. But it is very important to draw a correct kinematic representation, because if your kinematic representation is incorrect, then all the forward kinematics and inverse kinematics equations will be wrong. So how do I represent a spherical wrist? Spherical wrist is 3 revolute joints which are perpendicular to each other. And I'm going to show these 3 revolute joints in a configuration that actually makes sense from visualization point of view. So this is my first revolute joint. This is my second revolute joint. And this second revolute joint is perpendicular to this third revolute joint, which is over here. Now, please understand, this is in theory a wrist, which means the distances between the joint centers should be 0. But from analysis point of view, it doesn't matter. What I would do is, I'm going to assign some distances, and at the end, after all the homogeneous transformations and everything is solved, then what we will do is, we will call these distances 0. So this is my A1, this is my A2. So we will set A1, A2, and A3 is equal to 0 at the end. But to start with, I don't want to assume these to be 0. But if spherical wrist, we are saying spherical wrist, which goes without saying that A1, A2, and A3 are zeros. Now, why is this spherical wrist super important? Because if you look at one of the homework problems that I have assigned, which is like a Puma robot. Puma robot is a 6 degree of freedom robot. And why is it a 6 degree of freedom robot? Because it has a manipulator that comprises of first 3 joints, and then it has a wrist that comprises of last 3 joints. Please understand, whenever you have a manipulator that has more than 3 joints, the best way to solve that manipulator is just combine the first 3 joints, do the forward and inverse kinematics, then combine the last 3 joints and perform the forward and inverse kinematics. And I will take an example of 6 degree of freedom manipulator in next class. But think about this, like the manipulators that we have studied in the last class, a class before that, were the first 3 degrees of freedom. And this spherical wrist is integrated at the end effector of the manipulator. So total number of joints are going to be 6, manipulator 3 joints, and the spherical wrist 3 joints. Everyone understood this?
Do we have to combine them both again?
If you are given a 6 degree of manipulator, or if you are given an 8 degree of manipulator, or even if you are given a 12 degree of manipulator, you can't solve that manipulator in one shot. you can only solve 3 joints at a time. So you have, and you can't solve first 2 joint and last joint. These 3 joints needs to be connected to each other. Otherwise, transformations won't work. Everyone understood this? Again, there are some shortcuts that you can take, but we'll stick to a very basic procedure. That way, we don't have to learn too many things. It would be like one solution fits all. Okay. What do we do next? This is the kinematic diagram. Coordinate system. You want me to explain the rules, or are you comfortable with the rules by now? Comfortable? Okay. Z naught. Okay. Still, for my own satisfaction, Z2, Z3. Z needs to pass through the joint. X naught has to be perpendicular to Z naught and intersecting. And it needs to be perpendicular and intersecting to Z n minus 1. So here, as you can see, clearly my x1 is going to be like this, and the y would complete the triad. Y1. Now here we have a problem, and once again I will explain what the problem is. I can choose my x1 or x2 something like this, but please note this x1, if I were to choose this axis as x1, if I were to choose this axis as x1, this x1, even though it is, sorry, x2, even though it is perpendicular to Z2, even though it is sort of in the same line as Z1, it is non-intersecting. There is an offset. So please understand, the rule is not satisfied. Do you agree with me? What other option do I have? The other option I have is choose this as x2. Do you agree with me? But that problem doesn't get solved. Still, I have an offset between the Z1 and x2, right? So rule not satisfied. Everyone clear? This is an exception. So if I were to choose x2 like this, x2 is perpendicular to Z2, but x2 is parallel to Z1, and x2 is not intersecting with Z1. So clearly, this is a bad choice. Yeah. So can you see that this distance is A2? So if I were to draw the coordinate system, this x2 is perpendicular to Z2. But this x2 is intersecting with Z2. But this x2 cannot intersect with Z1, because if you look at the plane, this is the plane that we have. Okay, but this completes the triad. So y2. And here I don't have any problem. So I would say x3, and I would say y3. Now I want you to understand that x3 is perpendicular to Z3, x3 is perpendicular to Z2, x3 is intersecting Z3, and x3 is intersecting Z2. So all rules are satisfied. Everyone okay with this? Right hand coordinate x, y, z. Now why this is x, y, and z? Because remember, when you look at the graph paper, this always is x, you are going up, that is y, and z is coming towards you. And why thumb is X? Because that is the first axis, X. That is how you should remember. All right. Now 0R1. 0R1. All right. Tell me, oh, I would say this is my cosine theta 1. This is my theta 2. And this is my theta 3. Always these should be in the positive Z directions. Z0 is going up, so X1. Z1 is going out, so in this direction. Z2 is going in that direction, so Z2 like this. Okay, cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Let's not forget, we need to add the projection matrix. And projection matrix, remember, this is X1, Y1, Z1, X0, Y0, Z0. So X1 projection on X0, X1 projection on X0 is 1. Y1 projection is on Z0. Z1 projection, this is Y0. 0, -1, 0. So I'm gonna get cosine theta 1. Then I'm gonna get 0. Then I'm gonna get sine theta 1. I'm gonna get sine theta 1. I'm gonna get 0. And then I'm gonna get cosine minus cosine theta 1. This is 0, 1, 0. Agreed? Now I need to complete the homogeneous transformation. Please understand, this is the spherical wrist problem, which means my A1, A2, and A3, A1, A2, and A3 at the end will be 0. But I still want to work out this problem because this gives us an important insight into something called as the Gimble Lock, and I'll show it to you what that is. So if I say cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0, 1. Now, the most important thing to remember here is the distances here are in the 0th frame. So the X distance in the 0th frame is 0. The Y distance in the 0th frame is 0. And the Z distance in the 0th frame is A1. With me so far? Next part, 1 R2. Same thing, cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And now I need the projection matrix. And for the projection matrix, I'm going to have X2, Y2, Z2, X1, Y1, Z1. So, and this projection matrix is going to look like 0, 1, 0, 0, 0, 1, 1, 0, 0. Everyone okay with this? So after multiplication, there's gonna be minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0. Now, what I would do is, here is the problem. Please note, frame 1 and frame 2 do not satisfy the rules. So no, so exception to the rule. So what I'm gonna do, actually I did, is I moved my frame, which is x2, y2, and z2 onto x1, y1, and z1. So this is my x2, y2, and z2. This is my y2, z2, and x2. For practical purposes, I transferred this onto y1, z1, and x1. Are you with me so far? Which means, what that means, in the homogeneous transformation 1H2, my translations are going to be 0. Sine theta 2, 0. Cosine theta 2, cosine theta 2, 0. Sine theta 2, 0, 1, 0, 0, 0, 1. This will be 0, 0, 0, 1. And why is it? This is because frame 2 is moved on top of frame 1 to satisfy the rules. Now what I need to do is, I need to follow the same process and need to go to the next one, which is 2R. This is gonna be interesting. So 2R3. The matrix is going to be the same: cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1. Yeah, I'll answer that a little bit. This is 1, 0, 0, because Z3 aligns with Z2, X3 aligns with X2, Y3 aligns with Y1, or Y2. So, yeah. 0, 0, 1. The question on the Zoom. R3C should have a 0. Yeah. No, R3C should have a 0. What?
Yeah, 1H2, sir.
1H2.
0, 0.
Oh, yeah, here, that is, so this is the 0. Okay. So this becomes cosine theta 3 minus sine theta 3, then 0, sine theta 3, cosine theta 3, 0, 0, 0, 1. Now, here comes the most important part, 2H3. 2H3, the first 3 by 3 matrix is going to be cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1, 0, 0, 0, and there will be 1 here. Now remember, for practical purposes, Z2 is at the location where the frame 1 is. So basically, the frame, this frame has been moved on top of this frame. So what I want to do is, I want to draw this picture here. That way we are sort of clear how that transformation is. So nothing is happening to this frame 3. X3, Z3, Y3. But the frame 2, which was initially here, that got moved over here. So now this is my new frame. And why this movement was required? Because to satisfy the rules. So this is my X2, this is my Y2, and this is my Z2. Are you with me so far? And the distance between these two frames is along Z2, which is A2 plus A3. Are you with me so far? And it's in positive direction because to go from frame 2 to frame 3, I need to walk in this direction, which is same as Z2 direction. So I will have 0, 0, and last one will be A2 plus A3. Are you with me so far? So now you know the drill. If I want to find out the end effector position with respect to the zeroth or inertial frame, which will be 0h1 multiplied by 1h2 multiplied by 2h3. Are you with me so far? Now what happens here, that is super important, and I want to emphasize in spherical wrist because that is an important problem. If you take robotics 2, this same problem, which is called as the direction cosine matrix, that will pop up in every analysis. So here is what's going to happen. We are going to have 0R3 here. There will be zeros here. There will be 1 here. And here I'm going to have Px, Py, and Pz. Do you agree with me? For spherical wrist, if I make an assumption that all these joints, the first revolute joint, second revolute joint, and the third revolute joint are on top of each other, my distances A0, A1, and A2 are going to be zeros. Do you agree with me? So which means after multiplication, if I assume it to be a spherical wrist, my Px is going to be 0, my Py is going to be 0, and my Pz is going to be 0. Everyone understood this? I need to write this down. For spherical wrist, A0 is equal to A1 is equal to A2. Typically, there is some non-zero distance, but those distances are assumed to be very small. Or sometimes what they do is they perform mechanical compensations so that the effective distance is 0. For spherical wrist, since A1, A2, and A0 are 0, Px is going to be 0, Py is going to be 0, and Pz is going to be 0. But what I want to do is, I still want to perform this multiplication and find out the actual value of Px, Py, and Pz. And that will tell you some very interesting facts about the robots where you get degrees of freedom uh, maybe eaten, or basically that calls that maybe under actuation, or the robot does not perform the way it wants to perform. So I'm going to solve this problem as if A0 is a non-zero value, A1 is a non-zero value, and A2 is a non-zero value. But the most important part here, any question? A0 is, sorry, A1. Oh, I made a mistake. So A1, thank you. A1, A2, and it said A3, right? A1, there's A1, A2, A3. So, okay. So what I'm going to do is I'm going to assume some non-zero values of A1, non-zero value of A2, and non-zero value of A3, and try to find out the expression for Px, Py, and Pz. But you will observe, because of the robot configuration, something interesting would happen. Now, one thing I want you to understand, that this 0R3 is the rotation transformation. These three rotations, and that is absolutely very important. These three rotations and these three rotations are three successive rotations are about three mutually perpendicular axes. This is super duper important. And please remember this, because you will need this if you take robotics too. These three successive rotations are about three mutually perpendicular axes. Are you with me so far? Now, what I want you to do is, I want you to think about the global view. The global view is, after these rotations are done, I would get a 3x3 matrix that includes the first rotation, second rotation, and third rotation. Do you agree with me? And please remember, 0R3 has theta 1, theta 2, theta 3, but that matrix is the overall rotation from frame 0 to frame 3. Are you with me so far? That is nothing but your Euler's rotation. So the roll, pitch, and yaw that we talk about to describe the overall rotation is nothing but three successive rotations that are about three mutually perpendicular axes. Now, some of you may say, how many sequences are possible for three mutually perpendicular axes? There are 12 sequences, and that's why there are 12 Euler rotations. But in this case, in robotics, we actually use a very standard rotation. Sometimes if you follow Peter Kort's book, he will follow a non-standard rotation, but we are going to use the same standard rotation. But I want you to understand, the spherical wrist is nothing but the basis for the Euler rotations. And now you will realize what is the biggest problem with Euler rotation. This is the biggest problem with Euler rotation. I want you, in that figure, for a minute, visualize my theta 2 instead of 0, my theta 2 instead of 0 is 90 degrees. So I want you to understand that, and I will write this down. This is the problem with Euler rotations. And that is where quaternions comes in picture. So Euler rotations. What are Euler rotations? These are three successive rotations about mutually perpendicular axis. Now, here what I want you to assume is theta 2 is 90 degrees. And I'm going to draw the kinematic diagram with theta 2 is equal to 90 degrees. If I assume my theta 2 is 90 degrees, please understand my robot becomes something like this. And remember this is super duper important. Are you with me? This is my first joint. This is my second joint. This is my second joint. And this is my third joint. Now, the first joint is perpendicular to the second joint. And since I rotated by 90 degrees, what happened that my third joint, so I'm going to call this third frame or third joint, is now aligned with the first joint due to 90-degree rotation of second joint. Now, this is a big problem. Why this is a big problem? Because when something like this happens, 1 degree of freedom disappears. What do I mean by that? What it means is even though I rotate the first joint, or even if I rotate the third joint, my end effector position remains the same. And this is gimbal lock. Gimbal lock occurs when an aircraft is 90-degree pitched upward. So fighter airplanes or tactical airplanes do a maneuver like this, but Boeing 747 MAX or of the commercial planes will never ever fly like this. And the reason for that is the navigation system actually breaks down. It becomes a singularity because all of a sudden you lose degree of freedom. What it means, what is the meaning of losing a degree of freedom? So what do I mean by degree of freedom? Degree of freedom means that thing is free to move. Here, if the same motion for joint 1 and same motion for joint 3 is giving me the exact identical result for my end effector, which means one of that joint is not working. That means that degree of freedom is gone. Everyone understood this? So this is also called as the gimbal lock. Gimbal lock. And if you take my robotics 2 class, initially we will actually create a simulation for a vehicle, an airplane. And you will see when you use the coordinate transformation and apply 90 degrees, that airplane would just go up. So at that point, whether you perform rotation about yaw or you perform rotation about roll, it's not going to have any effect. Now remember this. This axis is yaw. So theta 1 is yaw. Theta 2 is pitch. And theta 3 is roll. And the sign convention that we are going to use, which is a YXZ sequence, theta 1 is yaw, theta 2 is pitch and theta 3 is roll. What that means, when pitch is equal to 90 degrees, yaw becomes roll, or roll becomes yaw, which means either yaw or roll disappears. And that is precisely the definition of Gimble Lock. Everyone understood this? So how do we handle Gimble Lock? For that, what we do is we assume, or basically we represent rotation as an axis and rotation about the axis. The idea is super simple, math not so much, but idea is 0R3 is the rotation from frame 0 to frame 3. Do you agree with me? What has happened that there were 3 successive rotations, and I want you to think about this because that will make conceptually thinking. There were 3 successive rotations. These 3 successive rotations were about the axes were perpendicular to each other. Do you agree with me? Now, what I'm going to do? What I'm going to do is I'm going to take the resultant. I'm going to take sort of resultant of those 3 axes, and I'm going to call that one axis. Okay, that axis somehow is the resultant of the axis of rotation. Are you with me so far? So I found an axis, and these 3 successive rotations which were about individual axes, I would find the resultant of these 3 individual rotations about the new resultant axis that I have formed. Everyone understood this? What that means is I don't need that big 3 by 3 matrix. I just need 4 elements. I need the axis, and you will always define axis in terms of x, y, and z, or in terms of basically in terms of unit vectors. So you need some I, some j, some k about that axis, and the 4th quantity is the rotation about that axis. And that is Euler parameter. That is Cottonian. Cottonian is nothing but a hyperplane. Why it's called a hyperplane? Because any plane outside 3 dimensions is hyper. We can't visualize it. So right now I have a plane. Instead of 3 dimensions, it has 4 dimensions. That's why it's a hyperplane. And what I have done to construct that hyperplane, I've constructed an axis and the rotation that constitutes that 4-dimensional hyperplane. If you want to see the visualization, go to something called as 3 blue 1 brown, and there's a fantastic video on Cottonians where it will be shown what Cottonians are. And as soon as you get rid of these rotation transformations and you have Cottonian, Gimble Lock goes out of the way. There is no Gimble Lock for Cottonians. Not only that, here, remember, for performing rotational transformation, we are actually taking a 3 by 3 matrix, multiplying that by 3 by 3 matrix, multiplying by 3 by 3 matrix. Remember doing this 10,000 times. This matrix multiplication for 10,000 times is going to take exponentially high time. But as soon as I represent these rotations as a Cottonian, I just have to perform multiplication between 4, 4, 4, 4, which means I'm saving 5 multiplications in every sequential operation. Remember doing this for 10,000. Now, that is the reason why when you play video games, that is the reason why when you take pictures for transformation, we don't use rotation matrices. Because when you rotate inside that DSP, that there is an algorithm that is performing this matrix multiplication. Matrix multiplication is time consuming and costly in terms of power and memory. So that's why they will always use quaternions. That's why when you play a first-person game, say, and then you are kind of shooting somewhere, then as soon as you move your keyboard, the whole scene changes because each and every pixel on your image is transformed to the rotation that the viewer is going through. Everyone understood this? But I mean, I will, if you need to know quaternions, please watch the video 3 blue, 1 brown. The video on quaternions. It's a 1 or 2 sequence video. But now please remember, Gimble Lock means spherical joint where the second joint is 90 degrees. How do we take care of Gimble Lock? Whenever you have a spherical wrist, they don't want the spherical wrist to achieve the singularity, which means that no Gimble Lock. So there will be mechanical stops that will prevent that joint from getting to 90 degrees. Remember this. What happens is, whenever that joint goes to 89, you can still calculate solution, but solution won't be numerically converging. If it goes to 91, solution, you will get a solution, but that solution will not be numerically converging. So what they do is, basically they approximate 89, if beyond say 87 degrees, they will say whatever it is 87. Beyond 92 degrees, or I mean between 90 and 92 degrees, whatever it is, they will say it's 92 degrees. Or the best, they will add some mechanical stops. So physically, that 90-degree rotation is not possible. So whenever you see a spherical wrist, there will be mechanical stops to prevent it from 90-degree rotation of the pitch. Now, what that means in terms of solving a forward and inverse kinematics problem. And what I want to do is, this would be a perfect time. I don't think I would be able to cover Skira, but I think I would still be able to discuss one thing. So what I want to do is, at this point, I want you to go to Canvas. So go to my issue. So please go to Canvas and I will share my screen. I'll try to share my whole screen. That way I don't have to go. So online students, can you see my screen? Go to my issue. Then I want you to go to robotic system 1. Okay. I want you to go to robotic system 1, go to modules, and then look at fall 22 lectures. And then there is a MATLAB script for Skira robot, and there is a MATLAB script for the spherical wrist. So click on the MATLAB script for spherical wrist. And then open this with MATLAB. So this is, let me set up the problem. In this problem, I'm going to assume a non-zero value of A1, A2, and A3. So imagine like as if you have a robot. Robot has 3 revolute joints perpendicular to each other. A1 is given as 100 degrees, 100 millimeters. A2 is given as 150 millimeters. And A3 is given as 175 millimeters. Everyone okay with me? In this MATLAB script, I have taken some shortcuts. So the previous MATLAB script which I showed you, they were like every step was laid down. step by step. But now what I'm going to do is I'm going to show you a sort of shortcut way, and this can be even made shorter next class. A shortcut way to solve forward and inverse kinematics problem. So we have a spherical wrist. In the spherical wrist, we have three joints. First joint is T1, second joint is T2, third joint is T3. Are you with me? Since I'm going to solve a forward kinematics problem and inverse kinematics problem, I have defined two values of T1 and theta1. They represent the same quantity. T2 and theta2, they represent the same quantity. T3 and theta3, they represent the same quantity. And then I have Px, Py, Pz's. Those are the end effector positions in X, Y, and Z. Everyone understood this? So clear? Then I substitute the joint values. And please check if my H01 is correct. Is it same as what I wrote earlier? I think so. Okay. Please check if my H12 is correct. Remember? H23, just see if it is correct. So what I can do is, I can actually highlight this and perform this multiplication. Are you with me so far? And I run this, and now all of a sudden, I get this big matrix. And this matrix is going to be a little bit intimidating. But this matrix is going to be your friend if you go to robotics 2. So let's clarify what this is. From here, so first row, first column, first row, second column, and the first row, third column, all the way to the third row, third column. This is your direction cosine matrix that indicates the rotation of frame 0 with respect to, let me put it this way. It expresses the rotation of frame 3 with respect to frame 0 about frame 0. Are you with me so far? That's why you got this theta1, theta2, theta3. And the last part, I want you to notice that there is Px, Py, and Pz. Are you with me so far? I have Px. Yeah.
P1 is equal to P3. Will we see one entire column going to 0?
Hold on. Hold your horses. So there is some little bit more discussion I need to do before I substitute T1 is equal to T3, T1 is equal to 0, T2 is equal to 90. All that mathematical jugglery or MATLAB experiments we can do. But let me make the things conceptually clear. So please understand that this matrix is the direction cosine matrix. This is a 3x3 matrix that includes all the information of rotation of frame 3 with respect to frame 1 in the frame 0 in the axis of frame 0. Remember, there are lots of axes floating around in between. We are not interested in that. We are interested in the first inertial frame because that's the only frame which is fixed. It's not moving. So every analysis, Newton's law, Lagrangian, velocity, acceleration, jerk, everything has to be calculated in the inertial or the 0th frame. The last part is Px, which is the end effector distance from 0th frame around x0. End effector distance of from frame 0 around y0. End effector distance in last from frame 0 about z0. But there is something missing in that equation. And I want you to see if you can spot what is missing. Theta 3 is missing. Are you with me so far? But if you look at the direction cosine matrix, theta 3 is present. Theta 3 is present. Theta 3 is present. Which means to find out this complete homogeneous transformation, I need to substitute theta 1, theta 2, theta 3. But to find position solution, I don't need value of theta 3. Everyone understood this? Now that gives you something else to think about. So I'm going to follow the same process. Now here is what I have done. I just used MATLAB and directly calculated Px, Py, Pz. So once I do that, then I just get, rather than copying and pasting, I get Px, Py, and Pz. That is the last column of H03. Now, what I need to do is I'm going to solve the forward kinematics problem. Substitute the values of theta 1, theta 2, theta 3, and find out the values for Px, Py, and Pz. Everyone with me so far? And that is, just substitute some angles. Theta 1, theta 2 is 35 degrees, theta 3 as 0 degrees. And then find out the value of Px, Py, and Pz. Oh, did I make a mistake? I didn't copy this. All right, run. Now, can you see that I got the value of Px, I got the value of Py, and I got the value of Pz. Everyone okay with me? Everyone understands this? So what is the process for inverse kinematics? Now, in inverse kinematics, ideally, I would find out the values of theta 1, theta 2, and theta 3. I would find out the values of theta 1, theta 2, theta 3 by equating Px is equal to the numerical value I got, Py is equal to the numerical value I got, and Pz is equal to the numerical value I got. Everyone understood? That's what we did in the last few problems, right? Now, but as I do this, see what happens. As I do this, I get some solution, but this solution is actually meaningless to me. And why is it meaningless? Because MATLAB is trying to use some transcendental function to find some solution, because MATLAB cannot find the solution using the regular techniques like trig substitution. Everyone understood this? Can someone tell me why is that? The reason for that is my T3 that is not present in my Px equation, Py equation, and Pz equation. Still, I'm forcing MATLAB to give me something, and this is what MATLAB gives. Everyone understood this? So what I should do is, there are multiple ways of solving this type of a problem. So I just use, instead of three equations, I just use two equations and find the unknowns that I can find, theta 1 and theta 2, right? And not worry about theta 3, because theta 3 value is clearly we cannot find out from inverse solution, and that's what you will see. So what I do is, the correct solution is theta 1 and theta 2, and then I find out the values of theta 1 and theta 2, and now I got the values. I substituted 0 and 35, but MATLAB gave me 0, 35, and 0 and minus 35. These two solutions are possible, and one of them is the input that I gave to the system of equations. Everyone understood this? So if you are trying to solve an inverse kinematics problem, before you set up the equations inside MATLAB, it's always a good idea to look at the equations for Px, Py, and Pz to make sure all three joint variables appear in those three equations. If one of the joint variable does not appear in those three equations, that means you have some type of degeneracy, and then you should just use two equations to find the two unknowns that are appearing in the three. Everyone understood this? So before blindly performing inverse kinematics, look at Px, Py, Pz to see if the joint variable that you are interested in finding out actually appears in the equation. If you don't do it, MATLAB will still give you a solution, but that solution would be meaningless. Everyone understood this? Any questions?
So these solutions is for theta 1 is 0, theta 2 is 35, and that will give you the correct end effector position regardless of what theta 3 is.
Yes.
Theta 2 could be anything.
0, 90, 180, whatever it is. That is actually rotating. Right? It doesn't matter.
Oh, right, it doesn't affect. Makes sense.
But it will affect the orientation.
Right.
All right. Now, what I want to do is I want to finish one chapter from Niku's book, which is called as the velocity analysis. How do you perform a velocity analysis? There are two types of velocities present. One is the translational velocity, and the second one is the angular velocity. Do you agree with me? So what is the best way to find translational velocity? You have the displacement equation differentiated. So you have the displacement equation for Px, you have the displacement equation for Py, and you have the displacement equation for Pz. Do you agree with me? So what we do is take that equation and differentiate it. Ooh, I did differentiation long time ago, right? So for that, what we do is we use MATLAB. So for velocity analysis, theta 1, theta 2, and theta 3, they change with time. Do you agree with me? Theta 1, theta 2, theta 3, they change with time. So time is an independent variable. Theta 1, theta 2, theta 3 are dependent variables. So I have defined my new symbolic variables. Why new symbolic variables? Because my old symbolic variables, they did not have time. So my new symbolic variables for velocity analysis is theta 1, which is different than t1 and t1. Theta 1 is a function of time. Theta 2 is a function of time. Theta 3 is a function of time. And since my Px, Py, Pz do not include theta 3, I just replace Px, T1 and T2 by theta 1 and theta 2, Py, T1 and T2 by theta 1 and theta 2, Pz from T1 to T2 get replaced in theta 1 and theta 2, which means my Pz new, Py new, and Px new will now be function of time. Are you with me so far? So when I do this, oh, sorry, I forgot to add symbolic value. Now, which means I got these displacement equations wherein theta 1 is function of time, theta 2 is function of, Py is function of time, Pz is function of time. Do you agree with me? And how do we find velocities? Differentiate with respect to time. And we are done. Clearly, these equations are long and intimidating, but I have no intention of solving them. I'm going to use MATLAB to solve this equation. So you have cosine theta 2, sine theta 1, and then you have that term which is diff theta 1 comma t. This is nothing but theta 1 dot. Then I have something here. This is theta 2 dot. Then I have something here which is theta 1 dot, theta 2 dot, and the last equation just has theta 2 dot. Are you with me so far? These equations can be written in matrix form. Are you with me so far? Now the second part, okay, before I go to the second part, I don't think I'll be able to finish Scala. But before I go to the second part, which is the angular velocities, trust me, you already know. I'm just going to write the expression and you're going to say, oh, wow, this is so simple. Before I go to angular velocities, any question about the MATLAB code or what I did here? My strong recommendation to you is play with this code. Remember, theta 2 is pitch. Substitute that is equal to 90 degrees. See what happens. Make theta 1, which is the yaw, and theta 3, which is the roll, make them equal to each other and see what happens. And you will see a lot of insights from this direction cosine matrix. Whether you want to do computer vision, robotics, inertial sensing, navigation, SLAM, tracking, then direction cosine matrix is always going to come everywhere you go. Roll, pitch, and yaw, they will always bother you. Gimble lock will always trouble you. Anyway, before I go back onto my whiteboard, any question about the code?
In order to get velocity values back from the final equation, we need to know theta dot.
Yes. For that, right now you can say theta 1 dot is 0, theta 2 dot is 0, which means my velocities are correct. Yes.
Are there any examples on MATLAB with the velocity code?
Examples on MATLAB. I just these two examples.
Like on Canvas, sorry. Like any codes that are uploaded with like the velocity stuff that we just.
Oh yeah, this and Stera code that I showed you on Canvas, both of them have velocity.
Okay, thank you.
Okay, any other question? And I will work out the Stera problem in next class. Okay, now here comes the second part of I think chapter 6 or chapter 7. So what I'm going to do is I'm going to go back to my blackboard, I mean whiteboard or the iPad, whatever it is. Okay, so now what I want you to do is I want you to understand after all that hard work in MATLAB, this is what I got. I got Px is equal to some function of cosine and sine multiplied by theta 1. So I'm going to just call this function A. Then I will get some function B multiplied by theta 2. There is no theta 3, so don't worry about it. This is Px dot, Py dot. I got C multiplied by theta 1 dot plus D multiplied by theta 2 dot, and I got Pz dot. These are the velocities, okay? These are the velocities. Is equal to, and the velocity just has one term, and I think that was just theta 1, right? Or theta 2. Just let me see here. So theta 3 so Pz dot is just at theta 2. So there is 0 theta 1 dot plus, I'm just gonna call f theta 2 dot. This equation can neatly written as a matrix equation. Oh, px py pz is equal to 1 2 3 4 5 6 a b c d 0 e multiplied by theta 1 dot and theta 2 dot. This is the equation for translational velocity. Are you with me so far? Yeah.
So why is the PZ's first term 0?
Because if you look at the MATLAB expression, there is no theta 1 dot. I mean, there is no term that is multiplying theta 1 dot, right? That's why I put it 0. Here comes the kicker. Px dot, and now you will remember this moment because I'm gonna cover what is E. E is 0 because silence, please. Silence. Here comes the kicker because I'm going to cover half of chapter 6 in one line. You will remember this for the rest of your life. What I want, just like translational velocities, I want angular velocities. Do you agree with me? So I'm gonna write down omega x, omega y, omega z. Do you agree with me? Somehow these omega x, omega y, omega z, these are the angular velocities, must be dependent on theta 1 dot, theta 2 dot, and theta 3 dot. Do you agree with me? Please remember, these rotational transformation, and here comes the most important word, they are assumed to be infinitesimal, which means very, very small. That's why we can use the matrix algebra or linear operation on these rotations. Since I'm assuming these rotations to be infinitesimally small at every point in time, I'm gonna say I have my first rotation encoded here. I have my second rotation, which is encoded here, and I'll tell you what I mean by that. And my third rotation is encoded here. My first rotation is about x naught, y naught, z naught. My all rotations are going to be about z naught, z1, z2. So this is going to be theta 1 dot, theta 2 dot, theta 3 dot. You agree with me? These individual rotations are about their individual z-axis, and if I want to transform those individual rotations to the global axis, I already have the solution. And after I perform this, and you don't have to calculate this, MATLAB will do this for you. After you do this calculation, you will get the expressions for angular velocity, which can be written as, just like translational velocities, as a matrix multiplied. I'm not done yet. Theta 1 dot, it will be something like, I'm gonna call this like theta 1 dot, theta 2 dot, and theta 3 dot. And this guy will be some kind of mumbo jumbo comprising 0R1, 0R2, 0R3 is called as the Jacobian. We stop here.